There are a lot of details of the Fermi-Dirac statistics and Bose-Einstein statistics that I don't understand. Now, I have begun to realize that a great learning technique is to begin by making a wild guess and then find out what is wrong. Making a wild guess is sort of like having a scientific hypothesis. Making a wild guess is sort of like having a scientific hypothesis. It might be nice if the guess is correct. Maybe a point of pride and you can move on with other things, but you'll actually learn more sometimes if you can figure out why your guess is wrong. My intellectual shorthand for Fermi-Dirac versus Bose-Einstein statistics is cards versus dice. Why? Because if I deal out a hand of cards from a standard deck, no two cards can have the same value. On the other hand, if I roll 5 dice, I can have several dice can have the same value. Okay, Wikipedia shows two differences in these equations. I think one of these differences is really important, and the other one is just a result of the two articles setting up the problem a little different. Under a Fermi-Dirac distribution, we have this equation where we've got 1, which means 1 mode per energy state, over e to the epsilon sub I minus mu over kt plus 1, and so there's a plus 1 in the denominator. This one has g sub I, so there's g sub I modes per energy state, and it's over e to the epsilon minus mu over kt minus 1, so there's a minus 1 in the denominator. The less important difference here is the degeneracy, g sub I, which I think is more of a difference in the description of the mathematics rather than a difference in the phenomenon. It depends on how you define very subtly different variables, as you can see below. Imagine that we have 3 particles with energy 5 units, with total energy 5 units. Because of quantum mechanics, they must appear in one of the following 6 configurations. 1 plus 1 plus 3 equals 5, 1 plus 3 plus 1, 3 plus 1 plus 1, 1 plus 2 plus 2, 2 plus 1 plus 2, 2 plus 2 plus 1. You could describe this situation as 6 individual energy states, which all happen to have the same energy, or you could call it a single energy state with degeneracy 6. You could describe it either way, but there's really no difference between there's no difference in the phenomenon. The more important difference between these two equations is between the plus 1 and the minus 1 in the denominator. So fermions are constrained by the principle that no two particles can occupy the same mode. So the probability of occupation for fermions actually never gets above 50%. That's the 1 over e to the x plus 1 graph. On the other hand, the bosons, with their equation 1 over e to the x minus 1, there's no limit to the number of bosons that can occupy the same state. Here you see that the occupation level goes up above 100% occupation and could go all the way up to infinity. Okay, now I'd like to take a closer look at the Fermi-Dirac statistics, and I'm not so much going to derive it because I don't at this moment know how, but just point out a couple of ideas that seem to be related. The partition function, the canonical partition function, and the infinite geometric series. You might learn about the geometric series in a college math or a high school algebra 2 class. It says if I take the sum of from k equals 0 to infinity of r to the k, I get 1 over 1 minus r. Of course, that only works if r is a small number between 0 and 1. I think it also works for r being between negative 1 and 0. Here are a couple of examples of the infinite geometric series. 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. Keep going with a factor of 1/2 between each thing. So it comes out to be 1 minus 1/2 equals 2. Here we have 1 plus 1/3 plus 1/9 plus 1/27 plus 1/81 with a factor of 1/3 in between each term in the series, and it comes out to be 1.5. Now that is if we start with this term being k equals 0. If we take the sum starting with k equals 1, we would start with the 1/2 instead of the 1. So if I removed the first term here, I would end up with 1/2 over 1 minus 1/2, which would be 1. If I remove the first term 1 here, I end up with 1/3 over 1 minus 1/3 equals 0.5. So let's say we were asked to do the following sum. Sum up all of the values of e to the negative kx from k equals 1 to infinity. If you write this out term by term, it may be easier to see the pattern: e to the negative x plus e to the negative 2x plus e to the negative 3x plus e to the negative 4x plus e to the negative 5x, etc. Okay, then, depending on your mathematical training, this might seem like an obvious step or a mysterious one, but in any case, you can pull the constant terms out of here, the 1, the 2, the 3, 4, 5, like so. So you have the 1, 2, 3, 4, 5. Okay, so now I can replace the e to the negative x with r, and it becomes the familiar geometric progression, r to the first plus r to the second plus r to the third, so long as r is less than 1. Now my end goal in doing all this, if you didn't know, was to get something that looked sort of like the equation for Bose-Einstein statistics. So Bose-Einstein statistics shows g sub I divided by a big number. This is a big number right here, minus 1. And what I got is r divided by 1 minus r, where r is a small number. How can I remedy this? The trick is to multiply the fraction by the same thing on the top as you have on the bottom. By dividing the top and bottom by r, we get a form more similar to the Bose-Einstein fraction. Okay, in particular, if we say that if we define r to be e to the negative e sub naught over kt, and it turns out that the sum of the associated geometric series, the sum from 1 to infinity of r to the k, e to the negative, I'm sorry, I should use a different variable there. So we'll define it as e sub naught over k sub bt. That's not very big, is it? So this is that k sub b is not, doesn't have anything to do with this k over here. So this is Boltzmann's constant, and this is just a counting index. I should use I or something like that. But anyway, if we go from 1 to infinity, summing up all of the terms in the sequence e to the negative e sub naught over k sub bt plus e to the negative 2e sub naught over k sub bt plus e to the negative 3e sub naught over k sub bt plus etc., etc., we'll get 1 divided by e to the power of e sub naught over k sub bt minus 1. So I can establish a method of deriving the sum of one thing adds up to another thing. If I take all of these terms, e to the power of negative e sub naught over k sub bt plus e to the power of negative 2 e sub naught over k sub bt plus e to the power of negative 3 e sub naught over k sub bt. Anyway, it comes out to this sum right here. But why should we ever want to sum up these terms? Okay, I don't exactly know why there's a pattern of 1, 2, 3, 4, 5 here, but at least I can give some kind of analogy to explain what we're doing. So what I'm going to start with is imagining a weird dartboard where we always hit the dartboard, but we just determine randomly where the dart lands. The probability of hitting the board in a particular section is proportional to the area of that section. But the area is going to be measured in units of maybe square feet or square inches or square meters. It really doesn't matter what units of measurement are used so long as the total amount is used in the denominator. I am carelessly measuring the areas of the regions on the dartboard. Here I get 1, 1, 3, say 5, 3, 8. Really doesn't matter what units I originally used so long as we're consistent. Here I defined 1 unit of area to be the area of this little blue section right here. Then everything else is measured in terms of that area. So this grayish or tan area, beige, is about the same as this blue area. This area is about 3 times as big as the blue area. This one's about 5 times as big. The total area is about 1 plus 1 plus 5 plus 3 plus 8 plus 3 is about 21. So the total area is, so the probability of a dart hitting in this green section, for instance, is about 5 out of 21.